Let's get started. It is my pleasure to start the hardware panel and to have all our speakers here from a wide variety of companies and institutes. We have Figgat from Quantinuum, focused on trapped ion quantum computing, Erik Eisenach from Quantum Brilliance and V-centers in Diamond, Pedro Lopes, neutral atom quantum computing, you know him, and happy to have you back, Pedro. Yashna Lekhai from the National Quantum Computing Center in the UK, and Daria Gusenkova from IQM, superconducting quantum computing. Great having you here. Let's start with some more in-depth introduction from all of you. Let's start with Erik.
Gladly. Yeah, so my name is Erik Eisenach. I'm a quantum engineer here at Quantum Brilliance. We are located I am located in Stuttgart, Germany. We also have a location in Australia, both in Sydney as well as in Canberra. We at Quantum Brilliance build quantum accelerators, which is basically our term for a smaller scale quantum computer using NV centers in Diamond. NV centers are essentially, they are a point defect within the diamond crystal lattice consisting of a nitrogen, hence the N, and then an empty spot next to the nitrogen, which we term vacancy. And those can act along with the nuclear spins that are both in the nitrogen as well as in the carbon crystal lattice as spin qubits. So before I started at Quantum Brilliance, I did my PhD at MIT under Dirk England. And I spent a lot of time at MIT Lincoln Laboratory working in the quantum sensing group there. So my background is actually more quantum sensing related really than quantum computing, but I was happy to make the transition and I'm glad that I did so. Yeah, so I think that's a good introduction.
There are some comments already. David says, who doesn't love diamonds or NV diamonds? Over to you, Pedro.
Okay, unmuted. Hi, everyone. My name is Pedro Lopes. I am a quantum advocate, or well, I'm the quantum advocate of QuEra computing. It's only me. That means that I am a sort of a community and partner manager. So I set up a lot of partnerships for research and for expansion of our application solutions, as well as I lead a lot of the community engagement activities, such as the ones that we are doing now, teaching like the tutorial that we did before, etc., etc. So at QuEra, we do quantum computing with neutral atoms. We are so far the only company that actually has put this technology in the hands of people via our services that it can be deployed on AWS. So anyone can access it. And it's a lot of fun. We are very excited about neutral atom computing. So many people probably started hearing more and more about the topic between last year and this year because things are moving very, very fast. It's nice. I didn't know Erik had been a student of Dirk. So Dirk is one of the founders at QuEra. And yeah, so here I am and happy to chat and take questions, etc., etc. It'll be fun.
Thank you, Pedro. Daria.
Hello, everyone. Yes, my name is Daria. I'm a quantum device design engineer in the IQM company. This is an European startup for building superconducting quantum computers. And it was founded in 2019 in Finland. But since then, the company grew up a lot. Right now, we have more than 200 people in the staff. I work in the research and development department here in München. We have also other locations in France, in Spain, and in Singapore. I'm working on design of application-specific quantum processors. This we call the co-design approach. I will be happy to tell more during our discussion about this.
Great, thank you, Daria. Caroline?
Hello, I'm Caroline Figgat. I work for Quantinuum, which works on trapped ions. The virtual lab tour for Quantinuum was right before this, so this might be a bit of a review, but for anyone who's just joining, this company Quantinuum has actually both a hardware component and also builds quantum software. So I work on the hardware, building trapped ion quantum systems, and we have locations around the world. The two sort of lab hardware locations are both in the US. I'm based out of Broomfield, Colorado, and then the other one is Golden Valley, Minnesota. And then there are also locations for the company in the UK, and Germany, and Japan. I specifically am an atomic physicist, which is the sort of subfield of physics that relates to trapped ions. And I particularly work on writing software for control systems that actually sort of do the low-level software that that make the ion trap quantum computer actually perform the laser pulses necessary to perform the physics and do the quantum computing. I did my PhD at the University of Maryland, also studying trapped ions, and did my undergrad at MIT as well, actually.
Wonderful. Then we have Yashna, who has experience in multiple qubit modalities. Welcome, Yashna.
Hi. Yeah, so I'm Yash. I work for the UK's National Quantum Computing Centre, which is a government institute essentially, but we're here to sort of support the UK quantum scene and make ties to other countries' national labs and things like that. So we go all the way from the academic side, supporting our university academics, professors with their groundbreaking research, all the way to everyday businesses who might not know how they could utilize quantum, looking at like what sort of algorithms they would need to be able to use and sort of applications on that side. But yeah, so that's the NQCC. And then I work on the ion trap team. So we have a couple of different hardwares. The ion traps are there. We've got superconducting. We may have a neutral atoms section soon, but we are a fairly new institute. So the building behind me isn't actually completed yet. We're still in some temporary labs, but it's a lot of starting up, making sure we're ready, getting our cryo down pumped, things like that. But my background as well is actually nitrogen vacancy centers. So I did my PhD at Warwick. And yeah, so I've been around all of the different hardwares a bit. Looking forward to questions.
Great, thank you very much. Oh, and this is a very interesting composition of the panel because we have trapped ion quantum computing ×2 basically, but for Yashna at the National Quantum Computing Center, there are also other modalities. Then we have superconducting quantum computing with Daria. We have Erik, NV centers in Diamond, and then Pedro, neutral atom quantum computing. Let's start there, Erik. Just heard that you were with Dirk Englund, and then you decided, with whom Pedro is very familiar, and then you decided to go the NV Center direction for quantum computing. Why, and why do you believe in this technique?
Yeah, so it's a good question. So, I mean, my background was in quantum sensing using NV centers, so it was kind of a nice transition to go from something to be used as a sensor to something to be used in computing. I think that the NV Center is a really promising platform for quantum computing simply because it operates at room temperature, at ambient pressures, and so you don't need the overarching infrastructure that you need for a lot of other qubit modalities. The challenges are in scaling up, which people are working on. There's nothing necessarily in the realms of physics that stands in our way. Because of those factors, I think it's very promising.
Varda from India adds, I am placing my bet on trapped ions. Carolyn, could you share where are trapped ions the best and maybe even better than NV centers in Diamond? Who knows?
Yeah, so trapped ions do have a bunch of advantages to my view. So the biggest one is the qubits themselves are just individual atoms, and the properties of those are handed to you by nature. So, like the inherent sort of properties of an atom are not going to drift over time unless the fine structure constant of the universe is drifting over time, in which case we have other problems. But so our qubits are essentially perfect. All of our errors are basically from our controllers rather than the qubits themselves. And the controllers are, those are sort of in our hands, and there's always sort of additional work, additional engineering that we can do to make those better and better and better. So we see those as very addressable problems. And that shows up in the fact that like ions have sort of consistently been among the best in terms of qubit fidelity and gate fidelity. They've set a lot of world records over the years. But it's sort of like easy for us to get to higher fidelities faster, we think, and that we hope will continue. They're also fully connected systems. There's sort of a few different ways that you can connect ions, but with all of them, there are ways that you can have basically fully connected systems so that you can perform pairs of gates between any two ions. With the architecture that Quantinuum specifically does, it's also very straightforward to be able to do mid-circuit measurement and qubit reuse. So like in the middle of a circuit without destroying the quantum information on any of the other qubits, read out one specific qubit, maybe in ancilla, see what it says, and then do some operation conditional on that. That's really useful for things like for quantum error correction, for example. So those I would say are sort of the like some of the biggest advantages of trapped ions.
And Carolyn says she uses the perfect atoms from nature, basically ionized. Pedro, you use them as atoms. Can you beat the trapped ions with the neutral atoms?
Well, I guess that's time will tell. But I think that what I like about the neutral atoms and is that I would take exactly all the points that were mentioned from ions and I would repeat them, right? So qubits are natural, so things don't drift. The fidelities, so a lot of people think that the fidelities for neutral atoms are a little slower, a little lower than the others, but we have always said that it's just that the technology is newer and we had not spent time, improving those fidelities. And quite quickly, just this year, there were demonstrations of like 99.5 to qubit gate fidelities, and we are pretty sure that those will climb up further than that. We have all-to-all connectivity, and I think that what comes as extra points are two items here. One of them is that the scalability, right? So we can definitely in a single like field of view of in a vacuum cell, we can fit 10,000 or more qubits without needing to create interconnects. So this is like the structure, the architecture can go all the way to 10,000 before we start to need to worry about interconnections. And another thing that we quite care a lot about is that we believe that we have a solution for controllers, which is this atom shuttling property or process where we can move atoms into kind of a processing region so that we don't have to control every atom individually. So that's something that I see a lot in the superconducting architectures where you have cables to control every qubit, but I see that as like trying to change the TV channel with a controller that has a button per pixel, right? So a regular computer does not control every bit all the time. And I think that having a bus of information is something that's very important, and that's something that our technology has. So we think that it's really going to be scalable, and we believe that we're going to be one of the few technologies that will be able to test error correction empirically, different methods, without having to restructure the architecture.
Would be, very excited to see that. Daria, yours are actually most human-made, also very tunable because of that. Can you share more about the advantages of superconducting quantum computing? And perhaps also the approach of IQM, not only transmons, also unimons?
Yes, of course. So first of all, the superconducting quantum platform, I think we benefit most from the established fabrication techniques, which are already available in the industry, and we benefit a lot from these techniques. Then we also have an advantage that we can couple the qubits strongly with capacitive or inductive interaction, and this allows us relatively fast gates. Of course, there is still a problem with coherence, and as Pedro told, with controlling every qubit, but I think we can address these challenges in the future. And speaking of connectivity, that's a part of our IQM co-design approach. We're actually optimizing the hardware for a specific algorithm, and we also optimize the algorithm itself to run on the processes more efficiently. Yeah, so I still believe in superconducting quantum computers.
Amazing, and definitely taking rapid speed right now. Yashna, NQCC doesn't place a bet now, uses multiple. Can you share more about that and how governments can support quantum computing, industry, academia, etc. best?
Yeah, so so we started in, I think, 2019, and we did a big landscaping of the current state of affairs at that point. And it was decided that we would have some hardwares. So we chose ion trapping and superconducting as our starting point, just because they are, they've been there the longest. They have a lot under their belt already. So we could utilize the field already there. And we were looking at really particularly in the UK, what is the UK very strong at the moment? How many spin-outs do we have? That sort of thing as to what the NQCC should have in its building. But apart from that, it's sort of, you're right, no, we shouldn't really hedge a bet as a government, because if you're wrong, it might not go very well. But we want to make sure that everyone sort of has a fair chance, essentially. So we run a lot of we'll be running things like testbed calls and sort of lots of panels. We do hackathons and things like that, that should support not only the professors working in labs already set up, but new startups and people coming into the industry, sort of our PhD students or our mechanical engineers and things like that. Because I think there are a lot of, everyone said that there's something really specific about their technology that's great, but the underlying engineering, you kind of pass between each other as well. So, integrated photonics will help ion traps and neutral atoms, fabrication techniques will help almost everyone, better lasers, again, help everyone. So it's that sort of support that a government lab can give whilst not playing favorites to the hardwares.
Amazing. We have many, many questions coming in, really tens of questions. So I will just go for a rapid round now and shoot Caroline, Erik, then Pedro. The question is from Juliana in Italy. What are the main challenges that you're facing with your respective realization as far as scalability is concerned? Caroline, Erik, then Pedro.
So for trapped ions, I would say the challenges that we're looking at for scalability. Yashna mentioned integrated photonics. That's going to be a really important technology, I think, that will make it a lot easier for us to scale in terms of the optical controllers. That's sort of an emerging technology. So, we think that it's got a lot of promise, but of course, there's just a bunch of work to be done in that space. In terms of additional scalability, just for the system itself, there's sort of a few ways that people are looking at scaling trapped ions. Quantinuum specifically is using this, what we refer to as the QCCD architecture, quantum charge couple device, but it's this idea of you've got many short chains of ions, and then you can shuttle individual ions between sort of different zones in the trap, to perform different operations in different places, bring different qubits together. Similar to the shuttling idea that Pedro mentioned. So that is what Quantinuum is pursuing. Other trapped ion groups are looking at what's sometimes referred to as sort of a long chain architecture, where they have a single chain of many ions, 50 plus ions. And then the scaling from there is maybe looking at having several long chains and having interconnects of maybe photonic interconnects, maybe having multiple traps that connect in some other way. So for Quantinuum specifically, for us scaling up, that's looking at things like building basically larger chip traps. So the scaling challenges there, of course, are continuing to have really good trap design, continuing to refine, making sure that we've got really good electrodes with really low noise, and sort of building on all of that, controlling the number of basically the number of controls on those electrodes, right? As your number of electrodes proliferates, that's just more and more wires. So figuring out ways to keep that from, sort of increasing noise or just being just an enormous amount of wires to route around. We've got some techniques going there. One is you can actually you end up with a lot of symmetry in these traps, so you can actually wire together electrodes that do basically the same job and then have a single controller for those. So that's sort of one thing that Quantinuum is looking at. So those are, and then with that, of course, continuing to expand the transport capabilities of those traps and generating the waveforms in order to make that happen. So in general, just sort of system scaling with engineering around the control system. But I think those are—
Thank you, Caroline. I think we see that there is a great challenge and there is a place for everyone to work here. Erik, some challenges are different for NV centers. Can you share a little bit?
Yeah, absolutely. So before, in my introduction, I kind of mentioned very briefly that NV centers in Diamond, they operate at room temperature as well as ambient temperature. So in terms of scaling, those really, they help us out because they reduce the amount of infrastructure that we need to actually operate our quantum computers. So Yashna also said better lasers help everybody, not actually necessarily us. We can actually operate with an LED really if we wanted to. I've actually used LEDs in the lab to pump NV centers into the ground state, the spin zero ground state, which acts as basically your basis for computation. However, I mentioned also earlier that the nuclear spins is at least what we're using as a spin qubit in the NV center. So per NV center, you can maximally talk to maybe around 4, 5, 6 nuclear spins per NV center, which means that if you actually want to scale up the number of qubits in your quantum computer, you're going to have to start increasing the number of NV centers. And the way they talk to each other, so the way that you can run, the way you can entangle and run multi-qubit gates, between NV centers is they have to be dipole coupled. And a dipole field drops off as 1 over r cubed, meaning that they have to be very, very close together. When I say very, very close, I mean on the order of 10 to 20 nanometers. So because they are traditionally optically read out, that means that you have to find a way to selectively read them out. If they're within a confocal spot, so that's usually around the order of magnitude 1, 2, 300 nanometers. You have to figure out another way of doing this. One way forward is to read them out electrically. So they also have photosensitive. They produce photosensitive electrical currents, so you can actually use that to read out the NVs. However, the other front on which you have to work is actually deterministically placing these NV centers within the diamond lattice. So a lot of people they do this semi-deterministically by implanting NVs, but for really truly scaling up the number of qubits beyond, say, like 20, 30, 40, 50, 60, maybe even above, you can't really rely on these semi-deterministic methods. So we at QB are actually working on some deterministic methods of doing this. Yeah.
Thank you, Erik. Over to Pedro.
Sure, Juliana. So I think that scalability challenges are not really main challenges for us. As you are aware, our machines, they are already operating at like 256 qubits, and putting more qubits there is just a matter of more laser power, right? So it's just a milliwatt per atom that you want. So getting more stable lasers, etc. It's more like a supply chain issue than really a engineering or technical issue. I think that you'll be seeing these systems scale a lot in the very, very short term. I think, as I was mentioning as well, 10,000 traps is not something that is beyond a reasonable expectation for a reasonable time. So what is a focus for us then regarding scalability is not the matter of putting the atoms together, because that we already showed that we can. It's rather controlling them. So creating the control systems and control channels to be able to operate. So while most of the functionality has already been demonstrated in academic labs, no one has put all of those functionalities, like the 2-qubit gates, etc., into a commercial product, and that's something that we are working on. And something that I definitely envy Caroline and Quantinuum is the mid-circuit readout that we don't yet have. It has been just the last month, there was 3 or 4 demonstrations of mid-circuit readout with neutral atoms, most of them using ytterbium, if I remember well, the papers. We use rubidium, so our approach is slightly different. But there is nothing that really stops us from doing it. It's something that is in process. So you'll be hearing more about that.
Great. Daria, could you comment on scalability and also on Varda's question, when superconducting qubits have a higher error rate than other modalities, why are they basically the most popular modality right now?
Okay, so maybe I will start from the last question, how I see it. So superconducting qubits are relatively easy to control. We use microwave pulses to do single qubit gates and 2-qubit gates. And there are also several platforms on which people successfully show useful quantum algorithms already. And answering the first question about scaling up, I would say that right now we are limited by coherence of our qubits. This depends a lot on the materials we use during fabrication, because qubits couple easily to defects in the metals. And of course, cleaning the substrate and the interfaces between metals should help a lot. But I can see also another challenge. This is a crosstalk between qubits on the chip. I mean, the parasitic coupling between elements due to charge or current flow. And of course, this needs elaborate design practices.
Great. Yashna, I would like to ask a question from Mohammed Reza to you. Which modalities would you bet on for joining this panel in the future? Let's say next year, but then also in 10 years.
Oh, that's a really interesting question. So we have seen silicon come up, and I think one of the positives for that is we have a lot of the infrastructure already, thanks to all of the technology we've got. So they're making a lot of leaps and bounds. And, I think you could maybe have someone coming in from Microsoft with their Majoranas, but I think that's maybe still a little way off. Topological qubits are interesting. It's a really cool concept, but some work to do. But yeah, I think everyone kind of agrees we've got the main ones on lockdown, with a lot of money already being poured into something. You get results out, sort of thing. So if you've got tech supergiants pouring millions into superconducting circuits and ion traps, then that's what you're going to see the improvements in.
Great. Any input from others other than your own qubit modality? Please shoot.
Maybe photonics.
I was about to say that.
Great, I see nodding heads. Amazing. Then, which modality will be the one to reach the first practical quantum computer which can solve real-world problems earliest? I see you're ready to answer, Pedro.
Well, I would claim that our machines have already solved real world problems, at least in the physics community, right? So we have done simulations of critical phases in 2D that are pretty hard to simulate classically. We have discovered quantum many-body scars, which is something that was not known until people ran experiments. We have realized quantum spin liquids. So I would claim that we are already solving real-world problems just because I put physicists as part of the real world. I just happen to do that. Maybe I'm biased. But because of the scalability and properties for error correction, we also think that we will get there much faster than many people believe we will.
Amazing. What is your view on this, Caroline?
I would also say that our systems are also already solving real world problems. And I think that's actually at this, particularly when you include like problems that physicists are interested in, I think that's true of virtually all the platforms at this point. So at Quantinuum, we've certainly solved real world problems for various customers, which I can't necessarily discuss in detail, but as I understand it, we have had customers that have gotten real results from our system and seen benefits from them in terms of various academic results and for ions in general, not at Quantinuum, but there have been academic results of using a trapped ion quantum computer, for example, to simulate what we think happens inside a black hole with something called quantum scrambling. I was on a paper about that in grad school. There have also been various quantum chemistry experiments that folks have done. I know that our company also recently released a paper on one of our systems looking at sort of a slightly different way of approaching the topological systems and topological qubits. Sort of demonstrating future approaches for quantum error correction and other things that will continue to advance the field. So.
Amazing. I see there is a really good competition between trapped ion and neutral atom quantum computing here. Erik, can you share more about the quantum accelerator concept? And recently, one of your accelerators was installed also at a supercomputer center.
Yeah, so I was going to mention, I think that some of the use cases that we're targeting have less to do with how many qubits you can throw at a problem, and more about how you can interface smaller qubit systems with traditional computing systems, such as those that you would find at the supercomputing cluster. So we've installed a 2-qubit quantum computer or quantum accelerator, which is what we call them, basically an analog to a graphical accelerator at the Pawsey Supercomputing Center in Australia. And so basically what we're trying to figure out is how do our lower qubit room temperature quantum computing systems, number one, interface with classical systems? What kind of problems can they solve? Can they actually assist classical systems in solving traditional problems faster? And how do these systems actually just generally behave in a center like this? This is quite a noisy environment, a loud environment, a very busy environment. So just to try and study the effects of such an environment on even a room temperature system is really interesting to us. And then our company also just very recently put a paper on arXiv talking about classifying quantum utility applications, which goes just beyond quantum advantage or just before quantum supremacy or quantum advantage, however you want to call this, talking about how you would classify problems that can be solved with a quantum computer, regardless of the number of qubits, but at a efficiency level that goes beyond what you could do with a classical computing system. So if you're interested in that, I recommend just searching quantum utility and quantum brilliance, and you should be able to find it quite quickly.
Yeah, there is also a question about, do you think your quantum computers will be particularly good at a certain application and maybe better than other types of quantum computers? Could you comment, Erik?
Yeah, so I think because we're very early on trying to interface them with classical computing systems, there are certain quantum algorithms like VQE, which kind of lends itself to this type of kind of hybrid computing system. And I think in particular applications that can benefit from these like hybridized approaches, I think our quantum computer will absolutely excel in.
Yashna, how do you view this, having multiple modalities at NQCC?
I think the most important thing is that we don't really have a good definition of quantum advantage yet. And all of these wonderful companies, they're all doing great work, but all of their benchmarks are very different. We don't have the right set of benchmarks like we do in classical computing yet to really pit one against the other. I think it would be probably quite unfair to try and do it. And we probably need to come up with some better benchmarks to really see who's going to get quantum advantage before the others. And I do think it might depend on your application as well. There's nothing to say that one type of algorithm will reach quantum advantage, but it will only be for one very specific reason. So you can't really say too much, I think. But
right now, quantum annealers are used a lot for optimization problems. Do you see a place for quantum annealers in, let's say, 5 or 10 years when the gate-based quantum computers are more evolved? Open for anyone to comment.
I think so.
I am pessimistic.
I think if they're good at a particular item, they're good at simulating. They'll always be good at simulating. And they might have other advantages. We're not just looking at purely how good is it mathematically. You could look at sort of cost effectiveness, how much energy they run, things like that. We should be looking at as well, not just can it solve the most difficult problem. So I think they'll definitely have a place.
And also
so that was actually going to tie into my previous comment. So going just very briefly back to the point of quantum advantage. So I think that many people define quantum advantage as having reached a point where you've developed a quantum computer that can solve this very particular problem quicker than probably the most powerful classical computer in the world. And so we actually like to use the term quantum utility, where basically you have a quantum computer that can solve a particular problem at a faster speed or faster or higher efficiency, maybe even an energy in kind of concerning energy efficiency than a classical computer of comparable size, weight, and power. So I think that is something that I think if people were to be more clear about defining quantum advantage in that way, maybe even using different verbiage, I think you'll start to see maybe a little bit more uptake.
Pedro was pessimistic.
Yeah, I'm pessimistic. I think that I agree that it's not all about speed. I think that we should really start being a little more deep about what's the use of a quantum computer and not reduce it to speed all the time. I think it's past time we do that actually. And start thinking of kind of what are the new use cases, the new things that are going to be allowed by quantum computers that are not done simply today, right? So it's about change. It's not about speed, right? Now, given that, I am pessimistic about the annealers exactly because of that, right? Because what they aim at is at speeding things up. And I think that it's hard to get the quantum speed up that the annealers are aiming at. Like, the way that they're built today, I feel like they have not been able to show quantum effects for speeding up. So it's just that I'm feeling that so far they have been losing at their own game. And they are extremely complex and well-made machines. Okay, don't get me wrong. And I think that it's completely worth using them and seeing what can be done with them. But I think that in the long term, without fault tolerance and really aiming at a kind of exponential speed ups, if you are aiming at speed, I think it's going to be very hard.
If Yashna, if you would have infinite money for the UK, what would NQCC look like?
Infinite money. Oh, well, as a scientist, I would just have labs everywhere. I think what we would do is just try and support everyone we could. So we recently ran a sort of open call for a test bed, and we just don't have the money to fund everyone. But you know, there are so many good ideas, and it's so hard to write a grant proposal for something. You might miss out. So I'd probably have a lot of people going into our industries, a lot of people going into our labs, seeing what we've got, seeing what they've got, really trying to make sure everyone's open access for their research as well. So if we could pay for that, that would be great. I know you've got like IP walls and things, but yeah, more collaboration. I think we should spend more money on.
Amazing, even among all the different qubit modalities. There is a question by Juliana. I don't know if I can dare ask it, but taking into account your qubit modality, how many years will it take to have fault-tolerant quantum computers? Anyone who wants to put some bet for their own, we can crop this out on YouTube. I expect some really bold answers from some of you.
I'm not positive I can comment that in public, so we do have a roadmap and I cannot mention it.
Yeah, I fear the same. But one can always ask, amazing, okay, indeed, Varda, we should have
if I can add a comment, right? If we have a roadmap, that's probably not 20 years, right? Because it's very hard to imagine what's going to happen 20 years from now. So that's what the way you should read my answer, right?
Right. And at least being at NIST myself, we take into account, yeah, in 10 years, everything needs to be ready for the post-quantum cryptographic age. And by then, who knows if Shor's algorithm can crack encryption. Let's move on to some career and workforce related questions. Daria, would you like to share more about your career path? And we'll ask that to all of you and then go more into what kind of skills are needed in the workforce for working at your company and beyond.
Yes, gladly. So I started as a radio engineer during my bachelor studies, but then I was so excited with experimental physics that I decided to change the topic. And then on my master and PhD, I did quantum physics. I was in the group of Yuan Pop in Karlsruhe Institute of Technology for the PhD. And I was working on different types of coupling between qubit and readout resonator to perform more quantum non-demolishing readout and to get a higher fidelity. And then just after my PhD, I found a place here in IQM. So for me, the transition from academia to industry was very smooth. I'm still working in my field and still in research and development department. So that's why for me, the transition was very smooth.
And commenting on this transition, what are differences you notice between industry and academia?
I would say now I have to set my priorities more strictly because there are so many open tasks and it's impossible to do everything. So yes, I have to be very strict with myself.
Great. I would love to hear from you, Carolyn, also about your decisions on your career path.
Yeah, so I actually got interested in quantum computing fairly early. I think I read an article about it in like 9th grade or something and was like, oh, this is interesting. Went to college at MIT and you know, freshman year I was doing like, oh, I don't know, like was telling myself I was undecided, but it sort of quickly became clear that like, no, like this quantum computing thing really is cool. And physics is also cool. And I also decided like, oh, well, you know, if I want to do quantum computing, 18-year-old me logic was like, well, then clearly I should study quantum and also computing. So I dual degreed in physics and computer science. I'm also like interested in coding and enjoy that. And I'm interested sort of in computers in general. So that ended up being a pretty natural fit for me anyways. And then I actually applied to grad school, got in, and then deferred for a year and worked as a software engineer for a year, which provided some sort of useful additional skills, was sort of a nice break from the school thing, and also meant that I had a bit of a like cash, or like basically had some financial resources going into grad school, which of course doesn't pay very well, and then studied trapped ions for my PhD, and particularly like lucked out, I think, really, and landed in a lab that really was doing some basically the first programmable trapped ion quantum computing system. And then once I graduated there, was able to go straight into industry. So I've been at Quantinuum and its predecessor when it was part of Honeywell since I graduated grad school.
Amazing. Actually, the fight is still going on Discord. Who votes for neutral atom, trapped ion, and V-centered in diamond superconducting, silicon-based? Can you all please share on Discord? What are your opinions, everyone? Who gets the most votes? And then we'll share it at the end of this panel. Erik, could you share more about what kind of skills are needed in the workforce? What kind of people and skills is Quantum Brilliance looking for? And how to approach it?
Yeah, that's a good question. I think, I mean, in my opinion, I think having a large set of experiences is really helpful. Kind of being interested in things that are outside your regular area of expertise, because you never know when you're going to be solving a problem that kind of lies at the intersection between different fields. So not just always keeping blinders on, also kind of reading up and being interested in other things. I think this is another thing is sometimes you want to be creative in your solutions. I know this is not something that's usually attributed to hardcore scientists, but I think it's the truth. Having a certain level of creativity, which is fed into by all these different experiences that you've accrued and all this different knowledge that you have from different areas. I think having the capacity to work in a team is extremely important. You know, building a quantum computer is really hard, and not one person is going to do it by him or herself. So being able to work in a team, I think is very, very important as well. Among, you know, and then just obviously your very standard stuff, which is having a high technical aptitude, being interested in science and technology. I think those are probably the key points.
Excellent. And Pedro, also some questions were, do we need a PhD to enter this field? Can you comment on skills in general and this?
Yeah, I can comment. So I think that this question is very deep and we could spend a lot of time talking about it, to be honest. But at the moment, thinking of QuEra specifically, I can claim that there are some needs and job positions that are actually quite not obvious, right? You might be expecting, oh, you need to be a PhD grandmaster in rubidium, right? Like, but sometimes skills that we are lacking is like cloud engineers, like people that are able to create a highly efficient cloud architectures for deploying machines on the cloud. And if you are looking for a job and you have those skills, we are looking for people, for example, exactly with that kind of skills. Another thing that is coming up a lot is manufacturing, right? So a lot of the people that are putting together quantum computers, they are scientists with a lot of R&D in mind. And when you come down to create more machines, right? Create more machines, improve the efficiency of engineering and make this reproducible, reliable, quality control, etc., so that you can make more. Because reality is that we need quantum computers in the world so that quantum computing is used for something useful, right? So if we get to utility by majority of the world, if this cannot be like the LHC, that there is one in the world and only one, handful of people are going to use it. So we need a lot. And I think that we have not fully started seeing the appearance of people that are transitioning from the mindset, I like to do the research, because reality is that there's still a lot of research to be done. None of these machines are, already at their final stage. They all need a lot of research. So they attract a lot of people that are, brought in by that challenge. So we haven't seen the transition from that mindset to people that simply like, I want to build reliable machines, right? That usually the people that are interested in R&D look at that and say, right? That's not what I was born for. So those are a few items that I could mention. So to do the manufacturing, probably you will not need a PhD, but the stage at which we are right now, very possibly that's going to be necessary in the beginning. And until we get to the stage where you can just really transfer down the knowledge. But for cloud engineering, definitely not. There are many people that don't have a PhD and are working on that. And it varies a lot on position.
Amazing. Yashna, your advice to everyone who is on the quantum journey, some people starting, some people finishing PhD now, some people thinking PhD or entering industry. What message would you like to share with everyone?
Message. I think a lot of what Pedro said was actually really good. I think you're kind of right. At the moment, if you want to be on the building side, the hardware side, you probably do. But I guess particularly for the NQCC, we're really trying to get this idea of quantum skills as opposed to having a PhD. You take someone who's got 30 years of experience with RF technology and you tell them what you need to apply it to quantum systems. So, we've got a platform for learning the basics of quantum technologies and like what the block sphere is, etc. Because you don't need to know all the maths to be able to build a really good system. We have a student mechanical engineer who's helping us with our designs, and all the little things like how you do something, how you build something for cryogenic use is important in the quantum industry. So that's the sort of skills. I think it's like upskilling people that we already have, that are already experts, is something we can really do. And for people just starting their careers, and just be passionate. I think that's the most important part. So I did my PhD in nitrogen vacancy centers and then went, what should I do now? And I just applied for something, and it was because I was really interested in anything and everything to do with it. I wasn't afraid to get my hands stuck in, and you have a lot of transferable skills that you might not realize are transferable at this point. So aligning optics is transferable. That is a transferable skill between hardwares. And obviously talking, that's always important. But yeah, just be passionate.
Thank you for sharing that. Great. Daria, what is your message to everyone?
Maybe for people who start their career, it's good if you try different techniques. If you're at the university, if you also look at the other groups to see what they are doing, what are their methods, because right now there are plenty of interdisciplinary tasks, and yeah, that would be really helpful in the future if you gain as much knowledge as possible.
So thank you. And then Caroline, the last part of this panel, what would you share?
Yeah, I wanted to second what Erik and Daria said about the importance of teamwork and interdisciplinary skills, and being able to work with folks from different backgrounds, both technically as well as socially. Folks who can work really well in a team, like make the entire team better and make everyone on the team do better work. The flip side, of course, is basically jerks are negative force multipliers. If you're someone who doesn't work well with others, that sort of slows everyone else down. So yeah, teamwork super important. People skills, like just being able to work with other people well. In terms of technical skills, we definitely also need a broad range from of sort of educational backgrounds from, I mean, at Quantinuum, we have folks who graduated high school from obviously folks with PhDs. You know, as time goes on, often what happens is sort of the PhDs might come up with like the, you know, the version 0 of solving some problem, and then it gets passed on to engineers who are really good at solving that kind of problem. I like to make the joke that as a PhD, I am really bad at a whole bunch of things. I'm a terrible electrical engineer. I'm a terrible mechanical engineer. I'm a terrible optical engineer. I'm a slightly less terrible software engineer, but I have a whole bunch of background knowledge of all those things, as well as knowledge of the physics in front of me. And so I can come up with like some kind of solution, throw it together with duct tape. And then one of the really nice things about working in industry is we do have these engineers who are really good at taking my like terrible duct tape solution and making it actually robust, more efficient, and actually work really well.
Amazing. Thank you all for sharing this input together. It really gives a great overview. And this already brings us to the end of the panel, although we could continue for half an hour, 1 hour days, because this really exciting discussion won't end the next 10 years or even 20. Pedro, Carolyn, Erik, Yashna, Daria, thank you very much for this great panel. We will be in touch. We have some requests for several of you to come for actually a separate lecture to tell more about your research regarding black holes or the axial technique, NV centers in diamonds, the role of the government, the specific type of superconducting qubits. We will be in touch. Thank you very much for these amazing contributions and great panel today, and have a great rest of the day.
Thank you. Goodbye.
Thank you. Great to be here.
Yeah, thank you. This was a lot of fun.